Hello everyone, this is Karthikesh Srivastav. I'm a candidate master on code forces, 5-star on CodeChef, ICPC Kanpur Mathura Regionals 2020 rank 27 and global rank 251 in Google Kickstart Round A 2021. And today I'm going to discuss the problem compare those strings, which is asked in Starters 18 November 2021. The difficulty level of the problem is simple and the prerequisites are none. So now let's move on to the problem statement. So, chef has two strings A and B consisting of lowercase alphabets. So basically there are two strings A and B. Each of them consists of only lowercase alphabets and both of them are of length n. Help chef find the number of indices I such that I is less than equal to n and greater than equal to 1 and the string is starting at index I and ending at index n, or basically the substring of the string A is starting at index I and going till the end, and the substring of string B is starting at index I and going till the end. The substring of index A is lexicographically smaller than the substring of index B, or basically the string B. S of I to n denotes the suffix of the string S starting at index I, which consists of the characters s of I plus 1, s of I plus 2 till s of n. String S is less than string T denotes S is lexicographically smaller than T. If two strings S and T have the same length n, then we can say S is lexicographically smaller than T if there exists an index I which is less than or equal to the length of the string S. And for every j less than I, S of j is equal to the T of j, and for that particular I, S of I is less than T of I. For example, ABC is lexicographically smaller than ACD because the first letter A is same, but the first position at which they differ, this particular string which is lexicographically smaller has a letter which is smaller than this particular string at the same position. And when we talk of ABC and ABE, at the first two positions, both of these strings have the same letters, but at the third position, when they differ, the string which is lexicographically smaller has a letter which is smaller than the string which is lexicographically larger. Okay, so in the input format, it contains a integer t denoting the number of test cases, and for every test case, there is a integer n denoting the length of the string A and B. We are having two strings. Now, the second line of each test case contains the string A and the third line contains the string B. We are given an integer n, a string A and a string B, each of length n. Now, for each test case, we have to print a single integer denoting the number of indices I such that the A of I to n, or basically the suffix of the string A starting at index I, is less than the suffix of the string B starting at index I. And the constraints are as follows. We have the number of test cases and n less than 1 e power 6, and the sum of n over all the test cases is less than 1 e power 6. So the optimal solution would be of order n approach. Okay, so let's move on to a bit of explanation. So if we are having two strings, suppose that this is the string A of 1, A of 2, A of 3, A of 4, A of 5, A of 6, A of 7, so on till A of n. Okay, so A of I denotes the ith character of the string A, and we are having another string B, B of 1, B of 2, B of 3, B of 4. Basically these are the characters of the string B, and so on till B of n, where n denotes the length of these two strings, which is same. So for any index I, let's assume that this particular index I equal to 5, if we want the suffix that is starting at this index 5 to be less than the suffix which is starting at the index 5 in the other string B, then for it to be true, we want a simple thing. If these two character matches, these two characters matches, these two characters matches, and these two characters matches, and if this particular thing differs, so we basically want that there should exist an index I, or basically an index idx greater than or equal to I, such that A of idx is less than b of idx. And if this is true for any index I, if this is true for any index I, then the suffix of I of the string A is less than the suffix of I of the string B. But wait a minute, there would be another condition. There should exist an index idx greater than or equal to I such that A of idx is less than B of idx. But there has to be one more condition. For every index idx2 greater than or equal to I and less than idx, A of idx should be equal to B of idx. Okay, so let's work on a few more things. If this is the string A4, A5 and A6, okay, and this is our string, there can only be three possible cases: A of I less than B of I, A of I equal to B of I, and A of I greater than B of I. So we will look at what are the things that would happen in each of the three possible cases. So we start from here. If this is equal, okay, move ahead. These two characters are also equal, simply move ahead. But if A of 3 is less than B of 3, then okay, then a suffix which would start at this index 3 and go till the end would definitely be smaller than the suffix which would start at this index 3 and go till the end. Because at the very first index, A of 3 is less than B of 3, and the suffix which would start at A of 2 would definitely be smaller than that which would start at the index 2 of the string B, because it is same for the first character, and for the second character of the suffix of a string A is smaller than the second character of the suffix of a string B. And for that, starting at this particular index, the first two characters A1 equal to B1 and A2 equal to B2, but the third character A3 is less than B3. So we would simply iterate using I and J, and if A of I is basically A of J is less than B of J, and we have started iterating from I, and for every index J, or basically for every index K less than J and greater than or equal to I, we found that okay, A of K was equal to B of K, but for the very index K, we found that A of K is less than B of K. Then we can be sure that any suffix that is starting at the index I plus 1, I plus 2, or till K, if it is starting at index I, then the characters from I to K minus 1 is same in both the strings, I plus 1 to K minus 1 is same in both the strings, and this particular character is smaller in the string A. Then the suffixes that are starting from index I or starting at index K would definitely be smaller than the suffixes of the string B. So we would add to our answer K minus I plus 1. But if this is not the case and A of K is equal to B of K, we would simply continue. We don't have to do anything. But if A of K is greater than B of K, then what we would do? Let's see. We are having A of 1, A of 2, A of 3, A of 4, A of 5, A of 6, B1, B2, B3, B4, B5 and B6. Suppose that these two characters are same, these two are same, these two are same, but this particular character is greater. Then for this suffix which is starting at this index, the first three characters are similar, but the fourth character of this string is greater. So this ain't lexicographically smaller. This particular string is lexicographically smaller. And for this particular string, the first two characters are same, but the third one, this particular string is greater. So this is also not lexicographically smaller. This is not lexicographically smaller. And for this string, starting at here, the first character is same, but the second character is greater in the first string. So this particular string is also not lexicographically smaller. And for this particular index, starting here, the very first character itself is greater. So this is also not lexicographically smaller. So we can definitely say that if A of K is greater than B of K, and before that we encountered every index where equality was held, then from that index I up to the index J, where A of J became greater than B of J, then for every index K less than or equal to j and greater than or equal to I, we can definitely say that none of the indices k satisfies this condition, as a of k comma n is less than b of k comma n. At none of the indices this condition would be satisfied, or basically a of k comma n and b of k comma n, where k is greater than equal to I and less than equal to j, where a of k is equal to b of k for k less than j and a of k is greater than b of k for k equal to j. So let's write a loop. Now what I'm trying to say, I would simply write a loop. This is an iterator over the first string. Now this would be an iterator over the second string, which is the string b. Now I would also take a flag variable. Let's look what we will do. If a of I, or basically, we will compare the jth character of both the strings, okay? If a of j is equal b of j, then we will continue. Or we can do one more thing. Let's derive the condition for the inequality, after that for the equality. Okay, if a of j is greater than b of j, then we can make sure you started your iteration from the ith character, the comparison from the ith index, and you came till the jth index, and you find that the jth character of the a string is greater than for any suffix from I plus 1 till the jth index would fail. Okay, so what we will do, we will just initialize I equal to j, because now we want to check from index I equal to j plus 1, and if we initialize I equal to j and break out of this loop, then I would be incremented here and would start from j plus 1. Now if a of j is less than b of j, then what we will do, we will again initialize I equal to j, but before this we have to do one thing. We would add to the answer j minus I plus 1, because we started iteration from index I, came till index j. Every character from I to j minus 1 was equal in both the strings, but the jth character was smaller in string A. So any suffix starting at index I or I plus 1 or till j would definitely be smaller. So we have to add to our answer j minus I plus 1 and initialize I equal to j and break, because we have to check for the suffixes from I equal to j plus 1. Else, if this is not the condition, then a of j must be equal b of j, and if this is the case, then we check that if j is equal n minus 1, then we make our flag equal to 1. Why? Let's assume that we are having this particular string and we started our iteration from this particular index. This is equal, these two are equal, and these two are equal. We came till the last index. Now we don't need to check for any other index, this index. If we check for this index, then these two are equal, these two are equal, these two are equal. If we check for this index, these two are equal, these two are equal. So there is no need to check for any other index, and we just initialize the flag equal to 1 and break out of here, because for every other index j greater than I, or basically k greater than I, the suffix would be equal, not lexicographically greater or smaller. So we would break out of this particular loop and we would check that if the flag has been made 1, then we break out of the main loop. So this is the approach to solve this problem. Let's move on to my code. Here is the code. Here t denotes the number of test cases, n denotes the length of the string. This is the string A and the string B. I initialize the answer equal to 0. I iterate from I equal to 0 till I less than n. I initialize the flag equal to 0. Then I iterate from j equal to I till less than n. If a of j is less than b of j, then I started iterating from I, okay, j equal to I. For every character from I to j minus 1, a of j was equal to b of j, because elsewise, if the inequality would have hold, then it would have broken out of this loop. But since it hasn't happened till now, so the equality has hold. And if a of j is less than b of j, then for every index from I to j, the suffix is starting at index I plus 1 till j has to be lexicographically smaller than the suffix that is starting at index I plus 1 or till j in the string b, because we know the condition for lexicographically smaller. The first I characters are same, or the first I minus 1 characters are same, and the ith character is smaller in the lexicographically smaller string. Else if a of j is greater than b of j, then for every character from index I to j minus 1, the equality was true. But at this particular position, the equality is false. Okay, or basically the equality is false. And what happened? The string A is having a greater character. Now at the very first position where these two strings differ, the string A is having a greater character, so it cannot be lexicographically smaller, it would be lexicographically larger. Okay, so we would break out of this loop, because for any index I, if we take the indices, if we consider any index I from I to j minus 1 and consider the string starting at that particular index I till n, then from that index I till j minus 1, I will only encounter equality. But at the very jth index, I will encounter an inequality. And the first inequality position, the character that the string A would possess would be greater. So the suffix would be lexicographically greater rather than being lexicographically smaller. And if j is equal n minus 1, then I started my iteration from index I, and all the indices till the end are equal. So there is no need to check for I plus 1, because from I plus 1 as well, all the indices till the end would be equal. From I plus 2 as well, all the indices till the end would be equal. So the suffix of either the string A or string B won't be lexicographically smaller or greater. Both of them would be exactly equal. And if this is the condition, then I initialize as z equal to 1. Because I have iterated from I till n, I don't want to again iterate from I plus 1 to n, I plus 2 to n, I plus 3 to n, because it would definitely give TLE, an order of n square approach. So in order to check it, I just initialize my z equal to 1, and if z is true, then I break. And here a of j is less than b of j, then I know that I know the answer for all the indices from I to j. So I have to get the answer from I equal to j plus 1. And the same is with a of j is greater than b of j. I know the answer for all the indices from I to j. I need to get the answer for index j plus 1 till n minus 1. So I initialize I equal to j, break out of this loop, and here I would be incremented, and it would start from j plus 1 and go till n minus 1. After this, I print the answer. So let's try submitting the solution. And you can also see the advanced for loop technique in here. Basically, I have written the for loop in such a manner that it would iterate over the whole string or every character only once. I iterate until I encounter the equality. It's going like this: equal, 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 equal. I encounter an inequality. I just break over there. And after that, I don't start my iteration from I equal to 2. I start my iteration from I equal to j plus 1. And then I go on. And if I go till the end, and till the end the characters are equal, I initialize my z equal to 1 and I break out. So basically every character is traveled 1, and this has a time complexity of order of n, not order of n square. So don't get confused with this particular double for loop. This is a place where you might get confused or you might make an error, so you don't have to get confused with that. And if you don't initialize this flag equal to 1, then you might end up in getting a TLE. So that is also a place where you can make an error, so just don't do that. And you have to get your break statements here, because these need to be there, because you need to get the answer. Because at the very first place where there is an inequality, you know that if a of j is less than b of j, then for every index I less than j, for every index k greater than equal to I and less than j, the equality was true. And since this is the first place where this is unequal and the character possessed by the string a is less than that of string b, so string a suffixes would be lexicographically smaller, and here the character possessed by the string a is lexicographically greater than that of the string b. So the string a suffixes would be lexicographically larger, and since we need only the lexicographically smaller suffixes, so we don't add anything in the answer. But here we need the lexicographically smaller suffixes, so we add in the answer j minus I plus 1. So that is the approach, and after this we break out, and we have calculated the answer from I to j, index I to index j. So we initialize I equal to j and start calculating from I equal to j plus 1. And here is the same thing. We have calculated the answer from index I to index j, and for none of the suffixes they are lexicographically smaller, all of them are lexicographically greater. So we start calculating from I equal to j plus 1. So these are the respective approaches, and this is a useful condition for initializing the flag equal to 1. And I don't know why this is taking so much time. 1 minute. Okay. So this is the approach. Let's try submitting the solution again. It's taking a bit of time. I have submitted the solution before and this is correct, so there won't be any trouble. Okay, let me show you my accepted solution. So yeah, you can see that this is the same solution which I showed you. Let me show you the solution on the ID. So this is the same solution which I showed you or explained to you, and this is an accepted solution. You can see it from here. So yeah, this is the approach to solve the problem, and thank you for watching the video.